Everybody, I'm going to go through a little bit on IR here in this video. So just kind of an overview of what I kind of do when I'm looking at an IR. So you can kind of see how briefly I go about it. When we start getting into IRs in class, then we will start practicing this in class. But I know that a lot of you are having some trouble with IR right now. So I'm figured now is as good time as any to get started on it. So for me, IR, the thing that we want to keep in mind here, IR is just giving us functional groups. Okay, we are not going to be able to look at an IR and then put together a molecule and say like it comes from this molecule, and I know that for certain. That is not the purpose of IR. The purpose of IR is to get these big kind of functional group type questions. And I would say some functional groups are easier than others when it comes to identifying them in the IR. So there's even some functional groups that are more easily identified than others. Okay, and there's going to be a lot of functional groups that we might not be sure which one it is. We might think that, oh, well, we've got like some kind of carbonyl, but I'm not quite sure which one. And that's when you really need to have other types of analysis, such as a nuclear magnetic spectroscopy spectrum. That's going to tell you a lot more about the structural information of a compound. And you guys are going to be getting to NMR soon in the lab. But those are going to be the kinds of things that we look for to actually build the structure. This is just going to give us the functional group information and nothing else. Okay, so the main sections that I spend my time in, this is kind of where I look first. So kind of the 2700 to 4000. That's where all of the bonds to H are going to be. Okay, so OH, CH, NH, and you can see differences in things like an sp2 carbon to H versus an sp3 carbon to an H. So those are really helpful in helping us identify those. So that all comes from this bond. We're looking at kind of the frequency of a vibration of a bond. So two atoms kind of going like this. The reason that these ones are so far to the left and have such a high frequency is because we have a very large atom in comparison to an H. So that is going to be like, if you imagine a spring, you pull the H, it's going to snap back to the big thing really quickly. Okay. So then next in the list, we have triple bonds. So those are also going to be very, very strong bonds because we have a lot of electron density keeping those atoms together. So that's going to show up right around 23 to 21. And then finally, we've got our double bond section. Okay. That's where we're going to find things like carbonyls, alkenes. I would say the one that I spend most of my time looking for in that section is the carbonyls. That's generally what I look for. Alkenes can be a little bit hard to see, and imines, which is what this is, they're just not as common as carbonyls. So, and then finally the fingerprint region. I would not spend any time here really. Like I know that in lab you kind of talked a little bit about the CO bonds. I think it's really easy to misinterpret things in the fingerprint region because so much shows up there. So it's really easy to see like a strong peak at 1000 and just think, oh yeah, it's probably a CO. But there's a lot of other stuff that shows up in the same place. So it's very easy to misinterpret. So I just don't look here. Okay, we don't need to go into that zone. We can get information more clearly from other techniques that don't involve kind of guesses. Okay, we can have a lot more certainty. So that's kind of what the sections of the IR I look at are. So just looking at this, there's not a whole lot, right, that we're getting out of that. So just be aware of that. So this is the spectral reference table that I'm going to give you in class. I will post this on Moodle. I'm going to post the IR and the NMR table that I'm going to give you. So that you just have them now. So this just breaks down a little bit more detailed of those separate regions, right? So we have the bonds to H region where we can see the alcohols, acids. So that's all of our OH bonds, all of our NH bonds, and then all of our CH bonds, okay? Then we've got the triple bonds. So that's going to be the nitriles, the alkynes, the alkenes, and I would say the one that I tend to look for, I actually don't look for alkenes much in this region, but benzene. Ooh, that one really got away from me there. It's usually right around 1600. And it's usually quite strong. Okay. So strong just means it's going to be a pretty large, long peak. Okay. So I look for benzene a lot of times, but alkenes, like this region, is actually getting to be a little close to the fingerprint region and a little bit hard to look at sometimes. So it's kind of hit or miss what I find in there. So then the one that I do look for a lot is I look around 1700. Okay, 1700 is where I look for carbonyls. So that's kind of the middle range of the possible carbonyl area. So these are all broken up into, pretty small little ranges, but there's a lot of variation within that, especially when you look at conjugation. Okay, so conjugation, remember, is just a fancy word for, pi systems that are connected to each other. So for instance, I would expect this ketone, because it is in conjugation with that alkene, this is going to be about 30 less than a regular ketone. So if I consider a regular ketone around 1710, right? So then I'm looking at something that's 1680. Okay, so that's one of those things that it's easier to spot once you know the structure, but if you're not sure of the structure and you don't know that you have something that's conjugated yet, that can be kind of tricky to go like, well, I have any of these ranges plus like a subtraction of 30 that I'm looking for. So it can get kind of complicated. So I just usually look for the presence of a carbonyl. Okay, so I'm just looking for any C double bond O, and then I'm going to look in other places. To determine which one I have. Okay, so the NMR is going to tell you a lot more clearly, what kind of carbonyl you've got in your molecule. So I think the IR is really helpful in just kind of pointing it out to you that you should look for a carbonyl. Okay, so I'm just going to label this really quick. This is conjugated. Okay, and then there's a couple of specific ones for various cyclic carbonyls as well. Okay, so this is the only IR table that I'm going to give you. As you can see, it's pretty short. It's just one page. It doesn't have a whole lot on it. But we don't need to become experts at IR. We don't need to be digging through like many pages of tables, because it's just really easy to misinterpret IR because there is kind of a large amount of fluctuation, I would say, depending on conjugation and just bond strength and other factors. So we're just going to get the big kind of functional group information off of it, and then we're going to move on. So I just want to go through a couple of examples. So these are the IR spectrum that are in your lab manual. So I'm just going to kind of go through how I would look at these, and how much time I would spend, I think, is kind of one of the key things. So first thing, I kind of go left to right here. So I'm going to start with this big peak over here. So what that's telling me, just based on how large that is, that's an OH peak for sure, probably from a carboxylic acid. Okay, and you can tell all of this just by like comparing things to the table up there. I have most of it in my head at this point, so I'm not going to spend a bunch of time scrolling back and forth because it's just going to be annoying for you to watch. So then we can see like we have kind of that peak, but then we've got this one poking out the bottom. Okay, that is a clear sign of a peak overlapping where we've got this kind of thing and then it juts down and is jagged. So this one, if we look at where our 3000 peak is, There we go, perfect. So that 3000 line is my dividing line between carbon sp3 to H, and then carbon sp2 to H would be on the right hand side. Okay, so because this is just right below 3000, that's going to be my sp3 carbons. All right, so that's telling me that, you know, I might be on the lookout for some sort of benzene or alkene, but I actually don't think so, just because this looks like it's going to be the one OH peak, and then on the side over here, I've got my sp3. But that's not to say that buried under here somewhere there's not some sp2 carbon H's, but there's no way for us to see that at this point. Okay, then the other big one that I'm looking at is this guy right here. Okay, it's right around 1700. That's going to be a carbonyl peak for sure. Okay, and that's one, like, you could say, okay, it looks like it's right on 1700, maybe a little bit above. So you could dig through this and say, like, well, you know, it looks like it could be a ketone or an acid. So the acid and the ketones, keep in mind, they line up pretty much about the same. So using the kind of evidence that we have from the rest of our spectrum, if we have this as kind of a guess, that would make sense that we probably have the carbonyl of that acid somewhere, right? Okay, so that's really kind of what we're looking at here. What was I gonna say? So when you're looking at an IR, you want to make sure that if you have this kind of guess and you're saying, I think that it's probably a carboxylic acid, you should make sure that the data backs itself up. So if you're saying, I think there's a carboxylic acid because I'm seeing this OH, we should be seeing that C double bond O somewhere, and we have it right here. Okay, so that's kind of, we want to just make sure that everything agrees. So let's move on to B. I might not do all of these, but I'll do a few. Okay, ooh. I'm gonna try to draw my line. Thank goodness it does it for me. Okay, so using that line, and I would actually use a ruler or something just so that you can kind of see. But over here, since it's directly to the left of 3000, that's going to be my sp2 carbon to H. Okay, and then on the other side, we probably have some amount of sp3, because otherwise it wouldn't be there at all. So we probably have a little bit there. And then if I go on and keep looking here, I've got another peak at 1700. That's going to be my carbonyl peak. I've got a peak right at 1600. That's most likely my C double bond C. And that's probably going to be like a benzene or something. Okay, but I don't really know for sure, so a question mark is totally fine here. Okay, I think it's benzene, but there would need to be other analysis methods that we used to actually determine that for sure. And then all of this we just are gonna ignore. All right, let's do one more here. All right, so this one looks a little bit different than A, right? So if we kind of think about what A looked like, the large kind of broad peak was overlapping our sp3 carbons. This one is to the left of that, right? So if we look at our table here, so alcohols are going to be 32 to 36. Acids are going to be a little bit lower than that, okay? So they can still go to 36, but they start at a lower frequency and are just very, very broad. So if it's narrower and kind of to the left of the sp3 region, that's generally just going to be an alcohol and not an acid. Okay, and then let's draw in our line again right at 3000. All right, so then that is going to be our sp3 to H. And that's something that you're going to see that in most cases, right? Because we're looking at organic molecules. sp3 carbons with H's on them are very, very common When you don't have that, that actually tells you a whole lot about the compound and that you should not be drawing any sp3 carbons that have hydrogens on them. So that's a really helpful thing to think about. So we've got the sp3. We don't really have anything else. I'm trying to, hopefully that line is straight. And then afterwards, like all of this is just fingerprint. So we basically just have sp3 carbons with H's and an OH. Okay, so that's basically how I go through IRs. It's very, very quick. I probably don't spend more than 30 seconds on an IR at a time, because there's really just no need to. And you all will see that a lot more once we start using NMR, because you can get a lot more information and spend a lot more time with an NMR and actually have that time be useful. So as always, let me know if you have any questions, and I'll see y'all later.